It's one of those that you point here. Apparently, I think you don't point with a laser. You point with it would be a. Can you try?
Pointer serves as a shifter as well.
No, look. This is the pointer. You point there.
Επόμενο. Πίσω. Βλέπετε και από εδώ. Επόμενο πίσω. Και άμα πατήσετε αυτό, δείχνει.
Ωραία.
Το πάνω, με το λέιζερ.
Not the laser point. More modern.
Okay, thank you very much.
Okay, welcome everybody to this morning session. We have a first plenary talk by Ioannis Antoniou from the Aristotle University of Thessaloniki. He's also the president of the Hellenic Physics Association. And he will tell us something about the pathway to knowledge, learning versus learning or modeling. Okay.
Thank you for the introduction. As a physicist,
Is the microphone picking?
first of all, I would like to thank the organizers for this opportunity and the organization of this wonderful conference. The more smooth a conference is, the more effort lies behind. So, as a physics student, I was trained to learn essentially several classes of dynamical systems. And all our training was to understand how these systems emerged from observations, and then how to develop the mathematics to solve them and get results. Results means predictions verifiable by other experiments, new experiments. In the last years, last means beginning of the 21st century, we started to learn that machine learning can do the same job even better. So I was very curious to see if it is really so and to what extent it is really so. So, a brief historical presentation to put the things in context. The acquisition of knowledge is always the product of intelligence. And what means intelligence now? Prigozhin, my teacher, gave me this book long before the emergence of AI. He met Piaget in a joint seminar, and the definition that Piaget provided to intelligence is very simple and very clever at the same time. Clever means it does not depend on the way you obtain intelligence. According to Piaget, intelligence is what you use when you don't know what to do. If you know what to do, you do not have to be intelligent. You just do it. So intelligence is our mental response to uncertainty, because when I am certain, I know what to do. And complexity, as we know, is one of the key factors giving rise to uncertainty. So, as we all know, intelligence includes all these functions, commonly accepted in psychology as well as in AI communities. Reasoning, inference, and so on, decision-making, central point in this list of functions is learning. Why? Because with learning, you can do all the rest. This is what we learned eventually. Human intelligence actually developed three modes. The first mode was practiced before the 6th century BC. The model is that behind phenomena, there are gods or other powers underlying them, and as you have nothing better, you develop the ability to contact these deities and get messages from them. This proved to be inefficient. Inefficient means it gave wrong predictions. And at the 6th century BC, in Ionia, the shift from mythos to logos took place. This gave rise to scientific method, physics, mathematics, and so on, until the end of 20th century. This model had some difficulties, and a new approach to knowledge emerged. This method is independent of models. It relies only on data observation and learning mechanisms. So, modeling is replaced by learning. Before the 16th century, no reasoning is needed. The oracles are interpreted by priests and magicians. There is a reason to mention this because maybe this is one scenario after artificial intelligence. And interpretation methods are very different. They are practiced even now. Astrologers make more money than physicists. It's reality. We should not be afraid of this. We should understand the reason, but I do not understand completely the reasons anyway. So the concept of proof appears in the 6th century BC when Pherekides, the teacher of Pythagoras, asked him to establish a new science. The new science is called mathematics, literally meaning what can be learned and what can be taught independently of personal relations. And at the same time, in Miletus, Thales developed his famous theorems. We know everything about it. This is the algorithm which we call scientific method. In the beginning, we ask questions, we obtain data. Obtaining data is not the same as registering data. Registration is a key point here for the development of science, because when we started writing on scrolls, we were able to register more data. It is still not known what data Thales used to predict the eclipse, the famous eclipse with the Battle of Kyrros. From the data, we construct mathematical models, we compute with the tools of the model, developing algorithms and programs, and we give predictions which have to be validated by new data. If the validation is okay, then I think if the validation is okay, I'm sorry. Then we have new knowledge within the mathematical model. If the validation is not okay, then we obtain still new knowledge, the knowledge that what we are seeking for is not in the model, is outside the model. Then we repeat the same story till we obtain green light and proceed. This is very successful. It is in the curriculum of all physics departments. Newtonian dynamics, the prediction of Pluto, Neptune, asteroids, and so on. It was astonishing that no astrologer managed to do that. Astronomers used simply mathematics. They solved Newton equations, and they predicted precisely the location of Neptune from the disturbances of Uranus. Fluid dynamics, electrodynamics, thermodynamics, kinetic equations, Brownian motion, statistical mechanics. Statistical mechanics gave rise to entropy, which later interpreted by Shannon as information, and is the basis of modern knowledge society. Relativistic dynamics, where a universe is seen as a dynamical system, quantum dynamics, quantum information. All these achievements are based on a mathematical model known as dynamical system. And predictions are obtained by solving this mathematical model. There are 5 problems in this grandiose effort. The first problem is that mathematical models involve only numbers. But data are not only numbers, they are sounds, they are pictures, they are thoughts. How can we process symbols? In the early 70s, the method of symbolic dynamics emerged. What is symbolic dynamics? You split the phase space into blocks, into cells, and you observe the sequence of cells. Now, each cell is interpreted as a symbol. It works. It gives results. Physicians and biologists try to interpret the genetic code as resulting from such symbolic sequences. They failed. They didn't produce anything useful in practice. The second problem is that with the advent of the internet, the World Wide Web now has an amount of bits of the order of Avogadro number, 10 to the 26. It's an enormous amount. How we deal with this data? We could not do it with conventional computers. The third problem is discovered by Poincaré and was put in precise mathematical language by Hadamard. He realized that solving the model may give 3 difficulties. The first one is that the solution does not exist under the assumptions of the model. You modify the assumptions and then you get solutions. The second difficulty is that there is no one solution, there are many solutions. So you need a selection principle which is usually outside the model. And the third difficulty is solution exists, it is unique, but is unstable. This is what we call today chaos. Instability is a problem because we cannot tolerate the slightest error, either in the insertion of data or in the processing of data. So chaotic systems have the peculiarity that the amount of bits needed to go from one step to the next one is doubling. So very quickly, you reach the limits of every human computer. This problem appears in optimization, in differential equations, difference equations, and in inverse problems. Doctors use inverse problems, and they are faced with this difficulty. Of course, in the 50s, 60s, regularization methods were developed, but they are not completely satisfactory. The fourth problem is the existence of highly interdependent variables. This problem cannot be solved by conventional statistics. You need network theory. To some extent, network theory can give you the best answer possible, calculating parameters depending on the interconnectedness of the network representing the interdependence. And the last problem is that in real situations, we do not know the model and we do not have any idea how to construct a model. So these are the 5 problems which were realized by the end of the 20th century. What we do? We observe how intelligent beings solve similar problems. For example, can you please show the slide? Can you please show the slide? Can you please show the slide? You see this dog is catching the frisbee. It's a key example. Why? You may come back to the presentation, please. The brain of the dog is solving Newton's equations, because this problem you can give to first-year students to compute the trajectory. So the dog can catch the frisbee. The brain of the dog solves the differential equation. What is the mechanism of this elementary example? There are many examples. You know, you have several such examples. But this is a little spectacular. So we have to understand, if we want to proceed further and imitate the learning process of nature, we have to understand how this takes place. What is the mechanism? This question was raised in the early decades of the 20th century, and the results were very fruitful for science and society. I will briefly present these results. First of all, the definition of AI that was mentioned yesterday, that AI is an algorithm which can provide responses to questions which a human player cannot distinguish from a machine. So whether a machine gives you the answer or a human person is indistinguishable. Many people claim that the Turing test has been passed already. Other people claim they have not passed. Searle and others claim that the Turing test is irrelevant to intelligence. There are several arguments, not within the context of this presentation. So the first question is, where is the memory in the brain? Because the dog should have some memory of the observed trajectory, where it is. The first person to answer this question was Aristotle. He introduced the term engram. The visualization was that somewhere in the brain there is a plate with a substance that can be sensitive to writing. So, like for example, the honey and the solid honey, or the candle, and thoughts and observations are written on this substratum. It was a nice suggestion without any confirmation, but still it gave an idea. The concept of engram is still kept in the neurophysiological community. So Simon, in 1921, introduced two concepts. First, the so-called psychophysiological parallelism. That whatever I think is registered as neurophysiological changes. And conversely, neurophysiological changes may correspond to some change of my thinking, observation, so on. And given that, this became the prevalent dogma of neurophysiology. The next question is whether engrams, Simon kept the concept of engram, and it is still kept, and still, but now we know what is engram. He proved that engrams are not uniformly distributed in the brain. He didn't say how they are distributed, but he said that whatever is the way of distribution, it's not uniform. Then Hebb introduced the concept of synaptic plasticity, that the relation between neurons is not hard, it is changing according to the processing. The famous statement, neurons wired together if they fire together, it became now the dogma of both AI and neurophysiology. It has been experimentally observed and is the basis of neurocomputing. This plasticity does not appear in my machine. My machine hardware does not change according to the program that is running. This machine is changing. Whatever I think introduce changes in the hardware. Today, all this has been verified, and Cantel got a Nobel Prize for this result. And you can see in this reference what is the state of the art of the engram. So we believe that all concepts, all observations are registered, but we don't know if registration is complete. What means complete? Complete means that whatever you register is registered reliably. This is a mathematical problem which was resolved by Kolmogorov, generalizing previous results of Fourier and other mathematicians who proved the Weierstrass theorem on that every function can be represented as power series. Kolmogorov proved that, Professor Major mentioned this yesterday, he proved that every function can be represented as a convex combination of weights. Not always convex, you may not be convex. The sum of weights may not be one. So, mathematically, we can safely produce further. And if memory is registered on the weights, the links between neurons, then learning, which means acquisition of new information, should correspond to change in the configuration. And that is the definition of learning according to Kolmogorov. Kolmogorov introduced a class of stochastic processes. He called them innovation processes, and were developed in his school in Moscow. The idea is very simple. In the left, here you see, blue is my model, and orange is my observations. I observe from time 0 to time t, and I have a model which is satisfactory because the error is within acceptable limits. At time t, I give prediction, and I observe from t to tau. If the prediction is matching, the observation, I say that I have new knowledge. If the prediction is not matching the observation, as it is here, then I have innovation, I have error, and I try to correct the representation of knowledge so that this deviation here is minimal. That is the idea, Kolmogorov. It is not mentioned in all AI texts, but those who search will find this information. Based on this, Hopfield and Hinton got a Nobel Prize in 2024. What was their innovation? That they represented the neural network based on the Ising models of magnets, where the magnet corresponds to the neural net, the elementary magnets are the neurons, and the neural interaction is represented by the link correlations, which is the scalar product of two spins, as we learn in the statistical physics course. So the neural processing is represented as a set of nodes linked by some weights, and each node has an activation. Then activation is changing as time goes on. And the way of changing is given by this formula. The neuron K is receiving inputs from other neurons with the corresponding weights and activation, and it is collecting and summarizing them, constructing the sum of weight with its activation. And this sum is passed through a filter. Why it is passed through a filter? For two reasons. First reason is that if there is no filter, the brain will blow up. So you have to keep the input signal within the acceptable bounds. And the second reason is mathematical, and this gives the model of mind processing. The sum of weights with activations is corrected with some bias. You will tell me, what is so new in this representation? This is just multilinear stochastic statistical dynamics. Yes, it is. But nobody thought to apply this in the neural network. The bias represents the fact that each neuron should be activated. And from here, we see that the parameters are the weights and the bias. This is how you control the neural network. This is a picture from the Nobel Committee for Hinton and Hopfield. And the next question is how to correctly identify the network parameters from the error of prediction versus observation. The error is written mathematically in elementary time series analysis using several versions of the root mean square error or the absolute error. In the case of large language models, the error function is the information distance between the probability distribution I believe and the probability distribution I observe. This is the well-known cross entropy, which is the correction of Leibler entropy, Kullback-Leibler entropy, with the entropy of the input. So this is some elementary observation in information theory, which was initially not so much emphasized. In old books in information theory, you will see and discuss the mathematical properties of cross entropy, but no AI discussion. This became very popular after the LLMs, the large language models, and today this is the way to match the error. And after you define the error function, you employ the tools of optimization theory. Optimization theory is the theory which tries to find the state which gives minimal functionals. The functional is now this error, and the rest is what you find in elementary textbooks of optimization theory. It is important to emphasize that all differential equations are equivalent to optimization, starting from Fermat, Maupertuis, Hamilton. Instead of computing the solution, you find the function which minimizes the action functional, for example. Mathematically, they're equivalent. In practice, it depends on the problem. Some problems are easy to find directly. Other problems are easier to find using variational principles. Let us not forget that the eigenvalue problem can have variational solution. So, Kolmogorov observation of ability to represent data. Kolmogorov observation that knowledge or new information is represented by the change of weights. And the third innovation is the error function, and then the story goes back to optimization theory. What is not yet discussed is how to represent images, sounds, thoughts, numbers in a unified way. The machines do that today. How they do it? David Mumford got the Fields Medal in mathematics, precisely algebraic geometry, very abstract mathematics, at the age of 37. Then he was bored. There were very few surprises for his mind. So, after discussing with Grenander, he tried to answer this question, and he developed the so-called pattern theory. What is pattern theory? You identify patterns, several patterns, and you try to find the relation between patterns. This is not a simple task, and it is not reducible to the previous discussion. It is something completely new. Without this theory, LLMs could not operate. So his teacher, Grenander, published the book Calculus of Ideas based on pattern theory. If you wish to understand how machines learn pictures, sounds, texts, and compare them, this is the theory, this is the way. Okay, you understand this, but how you identify the relation between concepts. Mumford told us how to relate concepts. Newton just copied Aristotle's organon, and he wrote the concepts there as a graph. It was the first graph explicitly constructed. You can find this in Cambridge, in the address I mentioned. Now, this idea is developed now as semantic network. Semantic network gives the hierarchy of concepts according to different verbs. Shark lives in the sea. Shark has a spinal cord and so on. So all this information, which biologists, doctors have, is represented in terms of semantic networks, which are updated. For example, in psychology, the semantic networks of several diseases are updated every 10 years, even earlier. Now, how you do reasoning with pattern theory in semantic networks? Here, the key idea was given by the philosopher Wittgenstein. He said that the meaning of a word is its use in the language. What means use? He says very nice philosophical ideas, but the guy who actually defined the relation was Firth. Firth was a linguist who is famous for the statement, a word is characterized by the company it keeps. So, how you represent a word? As a list of features. Shark is animal, lives in the sea, and so on. So it's a vector. So the closeness of two words is quantitatively assessed from the distance between the corresponding vectors. What distance? Euclidean distance. Please. You wanted to say? Sorry. I thought, I'm sorry. Sorry. So, in this way, we can estimate the distance of words in everyday life. How? You count the texts or the speeches where the words are used automatically. And of course, the meaning is changing according to the usage. This was actually the key idea of Bob Koke. He was a student of mine in Brussels, who actually constructed the so-called compositional distributional model of learning, of meaning. And this model is now the basis of quantum intelligence. It works for both kinds of intelligence because he provided a new representation of all these networks using Penrose diagrams, which he originally introduced in general relativity. Bob actually showed that every matrix computation, all linear algebra, can be simplified in terms of these diagrams. And it is applicable also for classical flowcharts. So AI based on learning, as defined before, and accompanied by pattern theory and semantic networks, can do all the tasks that natural intelligence can do. You can buy software to do all these things. So this shows that AI was successful, and we shall see now how useful it is. So the previous algorithm for knowledge replaces the model because there is no model. The model is machine learning, and the rest is the same. So new knowledge means that knowledge is represented in the neural network of the machine or our brain. The same concepts are equally useful to neurophysiologists and computer scientists. Now we try to answer the 5 questions. The first problem of symbolic processing was answered completely by LLMs based on the pattern theory. ChatGPT, Gemini, and DeepSeek, all of them use these ideas where the error is assessed in terms of cross-entropy. That is the difference with the previous generation of neural networks. The second problem of big data has been simplified by learning and also by algorithms which reduce the dimension. The same strategy of dimension reduction can effectively solve the problem of high interdependence. It was partially solved by network theory, and it is even improved using learning. You can see all these networks are as learning processes and reduce the complexity. The fourth problem of the fact that we don't know the model cannot be solved with dynamical systems and is the only way to address it using neural networks. If you don't know the model, you have to find some neural network in order to represent what is happening in terms of the weights of the neural network and make predictions. So that's why we are so happy with AI. What about the posedness? If I have a time series and I would like to make a prediction, The first question is there any periodicity in the time series? If yes, I do not need any neural networks. Elementary statistical methods developed in the middle of 20th century are enough. We teach them in first, second year of the university. But if there is chaos in the time series, can I make predictions? And I repeat that in optimizations and inverse problems, this question appears and there is also chaos there. So, how to answer this question? We developed a simple strategy. We produce a time series from chaotic dynamics, and then we feed the neural network with the time series and ask the network to predict. But chaotic time series are contaminated by noise, so they are not reliable. So you cannot do it for any chaotic system. But we were very happy to construct a representation of simple chaotic maps, which is error-free, proven to be error-free. For the 10th map, the representation is based on representing numbers as the ratio of two integers. So a number is a couple of integers, and it happens that this map does not change this representation, and the increase of information is not exponential. So for this particular map, you can predict precisely. Same is true for the logistic map. The logistic map is informationally theoretic equivalent to 10th map. What means equivalent? They have exactly the same entropy production rate. And Kolmogorov proved that if two dynamical systems have the same information production rate, then they're equivalent in the sense that you write down the solution of one, write down the solution of the other, and the second one is a painting of the first. It's exact painting. So this is a concept of equivalent dynamical systems. They may appear differently, but they're equivalent from the information theoretic point of view, which means they produce information at the same rate. In practice, mathematicians call the systems equivalent. So we took a time series from this error-free computation, we fed it in the neural network, and we asked the neural network to make prediction. And we compare the prediction of the neural network with the prediction which is error-free. Now, if you put the system in a computer, it will still give you numbers. And you compute also the time where the trajectory is lost. This time is known as the horizon of predictability by Sir James Lighthill in 1986 in a famous paper in the Royal Society. He introduced the concept and he apologized to the general public for the errors which were propagated by mathematicians claiming absolute certainty. It's a nice paper. You will enjoy reading it. The point of this paper is the horizon of predictability. What is the horizon of predictability? It's the number of steps where the error becomes intolerable. So this is the mathematical definition. So you are supposed to have the real thing. You are supposed to have the computation prediction. You compute the distance. When it goes beyond the acceptance bound, this is the horizon of predictability. It is a theoretical concept which is approximated by the so-called Lyapunov exponent. Lyapunov exponent, as you know, is the exponent of the assumed local exponential divergence of trajectory. And it is usually expressed in terms of the number of Lyapunov times. Lyapunov time, as I said, is the inverse of the Lyapunov exponent. So in this case, we have everything, and we can compare. And this is the result of the comparison. As you see, up to a point here, the predictions of the neural network is the same with the prediction of the errors of computation. But at this point, the difference becomes significant, and therefore, this is the Lyapunov time of the neural network, the prediction of the neural network. What neural network we chose? We chose the echo state reservoir network. We chose the error state reservoir network because a careful reading of the literature showed us that these give, or they believe, it is believed that they give the best prediction of time series. Conclusion. Machine learning does not improve the predictability of chaos. Complexity as trajectory instability, it is also manifested in terms of ill-posedness of the optimization, which is done on the neural network. So this optimization is worse. Still, if we have nothing better, if we don't know the model, the neural network will give you good predictions. But they are worse than the predictions which you would do if you have knowledge of the model. That is the first conclusion. Second conclusion. As I said, the tent map and the logistic map are informationally equivalent. So I fit both time series in the neural network. Does the neural network understand the equivalence? Which is also computationally obvious to see in the conventional way, not by learning. And the answer is no, not at all. The machine is thinking that these time series are very different. This is also identified clearly when you see the hyperparameters of the network, which means how the network is representing the different time series. Empirically speaking, they should be equivalent. The machine learning claims they are not equivalent. Of course, if you don't know the model, you cannot claim such things. It is the first time that we have observed these things. Next point. Yes, this is the precise estimation in terms of multiples of Lyapunov time. So the machine learning discriminates equivalent dynamical systems. Yes, what I was shown previously is that if you have different time series originating by different seeds is you write the initial condition, you compute the trajectory. You write another initial condition, you compute another trajectory. So you feed the network with different seeds of the same system. They do not have the same horizon of predictability, which means that the machine is understanding patterns, and they only care about the complexity of the computation and nothing else. So the results are like that. The last question is, if we observe such things, can we relate the time series with the values of the hyperparameters which control the network at a given prediction? And the answer is no. All hyperparameters of the ISN are different for different initial data. The leaking rate, the spectral radius, the density, density is the density of the network considered as a graph. And the last thing is, in practice, there are also other results, but we have no time. Can we detect the optimal hyperparameters? Which means I have a time series, and I want to know which hyperparameters will give me best prediction. And the answer is no, it is not possible. They are distributed chaotically. Slight changes of trajectories give you enormous changes in the hyperparameter space. Very nice. That is what I can say about the comparison. The comparison fails in this point. All the rest are verified. And they are verified in a fantastic way. 2 months ago, Claude solved an open conjecture by Knuth. Knuth is one of the fathers of computational mathematics. Knuth himself wrote a paper saying that he is forced to change his opinion about AI. And this is a nice representation of this situation. We don't know whether the machine or Knuth will be the senior author in the paper. AI can do scientific research. Writing a paper is an algorithm. You get data, you formulate data, you write remarks, you write conclusions. Can this algorithm be learned? Yes. 2 papers presented last month in Nature. It can be done. All these results assume that the neural network is processing within a given mental model. It is not yet possible to train neural networks to go beyond the mental model in the data. So, although several mathematical problems have been solved by neural networks, they share the common mental model, usually combinatorial type of problems. So, for example, a neural network cannot get relativity from the discrepancies of the Michelson-Morley experiment. Neural networks cannot find the photon hypothesis from the deviation of empirical black-body radiation law with the Rayleigh-Jeans law. Consciousness is still out of the scope of neural networks. Still, we have a lot of work to do. Thank you very much.
Thank you very much. Very important talk. Any questions or comments?
Well, 2 questions. Short one, you mentioned at some point that all, let's say, flows, differential equations can be written as an optimization flow.
Yes.
So, is there a constructive output, let's say, to create maximum function for every system of differential equations?
Unfortunately not. There are theorems. This is a problem of the best mathematical theorems. They show you that this is possible, but they don't tell you how to do it. Yes. For example, in quantum mechanics, Feynman used this optimization algorithm, these famous Feynman diagrams, and he wrote a book, the famous path integral method. It seems that in quantum mechanics, it is more useful in practice. But in classical cases, I don't think there is a way to do it constructively. But you are sure it is like that. So it is nice to know that what you're looking for is there.
Because actually it relates to the second question that, let's say, So it seems that nature, let's say, law, prefers the variation of way of learning, summarizing, optimizing, and so on. While science, in the way predictive science, like Newton's law and so on, works with models which are mostly, let's say, the stationary points of the process, so of speaking, the equations of motion themselves. So my question is, do you believe that artificial intelligence will come to the point of proposing models, say, deductive models that summarize the whole of the empirical evidence in way fewer symbols, and so on?
It will be a great risk to answer this question, what I believe. I prefer to not believe, because results are so intriguing that people like Knuth had to revise their preconceptions. So I just want to mention that learning without understanding was also possible in ancient Greeks, the famous theory of epicycles. The solutions given by epicycles are mathematically the same with the solutions given by Newton's law. So why we prefer Newton's law? For one reason only, that with Newton's law we can discover Neptune from the anomalies of the trajectory of Uranus. With epicycles we cannot. That is the key difference between epicycles and dynamical systems. With neural networks, we are like the epicycles. We do not understand what is happening, but we still produce results. So I think these three questions, the task of developing a theory, an answer beyond the mental model, will shed some light to your critical question. I'm personally observing now. I'm very curious to see what's happening.
I will come to this idea of intelligence that you mentioned of Piaget, which I didn't know, and it's really very interesting. So let's think like Boltzmann and make an ensemble of things that we are ready to face in our daily life. Let's make an ensemble of things and then make a distribution. Now, most of the things are trivial and therefore probably are in the center of the distribution. And some of the things are in the tail of the distribution, like a roadway appears from nowhere, and we have to cope with it. I mean, Raoul Doral works with the edge of the distribution. So the question is, okay, can this be learned also? Because this is the edge of the distribution. I mean, we have means of addressing it. How learning affects the edge of the distribution.
In fact, what you said is the strategy of neural networks. As mentioned by Professor Meitner yesterday, they are called Boltzmann machines. The data they collect are whatever is uploaded in the internet. And they construct the probability distributions, and from these probability distributions, they give you answers. So the question would be relevant if the probability distributions have singularity, some long tails. And I have not seen such a thing yet, so I cannot answer the question. So all probability distributions are good, or they are constructed to be good. What means constructed? You know the Google algorithm, which was developed in the late 90s, was based on the so-called shrinkage approximation, which actually, if there are gaps, so the network is they're almost empty, because when you reach a website, and there is no other hyperlink, you just jump to another site. This you cannot see by observing the network. So Google introduced an algorithm which makes the network dense, so manageable, so you can compute the distribution. So all these networks are in practice constructed using some smoothing procedure, which is a variation of this shrinkage approximation of Google. So that's why I tell you I have not identified any singularities in the probability distributions constructed from the data of the internet. But the question is, of course, you know, it is a difficult question for statistics. But so far, I have not seen like that. If I will check this. I cannot answer the question because I have not seen such pathologies.
Any other questions? Comments? No, I think you have given us many ideas to think about with our natural intelligence. It's such a good topic to think about.
Thank you.
The second invited speaker is Professor Giorgio Tsironi, professor at the University of Spain. Professor George Tsironi is a leading figure in theoretical physics and one of the most influential Greek scientists in the field of nonlinear science, dynamical systems, statistical mechanics, and artificial intelligence, focusing on application in physics. Professor Tsironi received his PhD thesis from the University of Rochester and then held a research faculty position at San Diego universities, Texas, and also had some appointments in Harvard and Cambridge University. And he has been professor of physics at the University of Cleveland since 2000. His research spans condensed matter physics, nonlinear analysis, solid theory, complexity, biological physics, and materials, and also he received the Stephanos Pentecost International Award for his technical contributions to non-equilibrium statistical mechanics and nonlinear lattice dynamics. He has published more than 300 papers and also he supervised a lot of with thesis. In recent years, Professor Tsironi has been at the forefront of integrating artificial intelligence into the standard complex system. In the standard complex systems with applications ranging from cardiology to epidemiology, human detection, and quantum systems. Also, Professor Tsironi has a central role in academic leadership, serving as department chair, deputy director, and director of major research centers, including the Center for Quantum Complexity and Nanotechnology. It's a great pleasure to have Professor Tsironi talking about artificial intelligence in classical and quantum complex systems. Thank you very much for coming, for accepting our invitation, and to all this work.
Okay, thank you very much for this wonderful introduction. Most of it are lies, but it doesn't matter. I'm very happy to be here, and I hope, let me first find out how this works, okay? Okay, I know how it works, this one, and then I want to see the pointer. This must be the pointer. Okay, all right, good. Okay, I have been in Crete for many years. In the last more or less 10 years, I'm also affiliated with Harvard, and I have to admit that my connection with artificial intelligence somehow started in Cambridge, Massachusetts, because about 10 years ago, I attended a conference organized there. I didn't know anything about AI. Organized there and focusing on AI use in material science, and I just could not believe that machine learning and AI could have this kind of capabilities, and I really got hooked after that, and here I am. Okay, so the outline of my talk, I'll give an introduction and tell you a little bit of what is machine learning, and then I will go into complex systems and several examples, and I will go into medicine and quantum learning and things like that. But basically, the main question that I sort of, that I'm interested in is whether we can use the computer, AI, for instance, or machine learning, in order to learn solutions of physical primarily problems and use these solutions to extend into areas that we actually cannot have solutions. I'll be more precise very shortly. So of course, complex systems are everywhere. They range from, they range from materials. This is the famous twisted bilayer graphene that you twist it a little bit, 1 degree, and then becomes superconducting. You move away from this, it loses superconductivity. This is a magnificent system. Nobody understands it. It definitely has some form of complexity. We have the brain, of course, there's not much to say there, and we have the heart with its beautiful waves, this related to atrial fibrillation. So these are completely different systems. They share some common ground, and of course, the science of complexity, let's say, or people who are interested in nonlinear phenomena, they want somehow to understand them, to have some methods, perhaps common methods. So I will focus on 3 things here, which are dear to my heart: chaos, chimeras, and breathers, actually. Okay, and this I will use as sort of the backbone of my studies, and you will see as we move along. Now, I think physics and AI share something common. Okay, they both try to compress information. We have the world of 10 to the 23 particles, and we try to condense, some of this into Maxwell's equations or Newton's laws, blah, blah, blah. And this is some sort of projection, if you want, or packing everything into a smaller number of variables. Now, AI does a similar thing, and there is a beautiful construct, which I think is one of the most beautiful ideas in AI, which is called the autoencoder, and I will show you this very shortly, that basically tries to do the same thing. So in some sense, physics and, physics is some sort of autoencoder, in my view. Okay, so what is machine learning? Okay, so in traditional programming, we have the data, we have the algorithm, and we feed everything to the computer, and we get the output. Okay, now in machine learning, we have the data, and we have the output of the data. That is what they call labels. Okay, so its datum means something, and this is the something. And then we feed both the data and the context of the label or whatever of the data into the computer, and the computer spits out the algorithm. Okay, so the basic difference of the traditional programming compared to machine learning is that here we know we fix the algorithm, here we expect the computer to find the algorithm. Okay, so I have a very simple example just to fix things. So let's take a linear function, which is this one here. F of x is 0.2 plus 0.5x. Okay, the x is in front instead of behind. Okay, so I just make a table of this from 0 to 1, 10, 11 numbers, and this is the input, this is the output. So I have this simple mathematical function, totally trivial, okay? And I would like to see how I can discover this function through the data that I will give in the computer. Okay, so let's see how we do that. So we use what is called supervised machine learning. We have the input and the output. So these are the labels. So input is 0, 1.1, 0.2, etc. And this is the output from this function, which we know, of course, but we are cheating in some sense, but we have to. Okay, so what do? I construct a new function, y tilde, which so happens, I take it linear. I don't have to, but this is for the purpose of this very simple example, where I have W1 and W1x plus W0, and these are unknown. These are the connections that the previous speaker was talking about. And so what I want is I want to fix the input and make sure that the output that this function spits out is as close as possible to the real output. And in this process, I want to discover W0 and W1. This is what machine learning does. Okay, so I start with some random values, W0.4, W1.9, and then I feed in the inputs, and I calculate the loss. The loss is just the Euclidean distance between the real output and the fictitious output, the synthetic output that I'm producing. So now I'm spitting in the numbers from the left. I produce an output, okay? These are for, imaginary W0, W1, completely random, okay? So I get a new vector, okay, of values. I calculate the loss. I find the average loss, and I say, oh, this is 0.2. It's not good enough. Okay, let's go back and use this beautiful idea of backpropagation, change a little bit the weights. This is an algorithmic thing. And then let me calculate again. Okay, so now I have W0.14, W1.65. I calculate the new output. The loss is smaller. Okay, great. Now I continue backpropagation. I want to make it 0 if possible. Okay, so I keep doing this. So I'm changing the W's. I'm changing the weights here through this backpropagation algorithm. It's just a derivative, vector derivative. And then I keep doing that, and I get better and better W's. You see now, remember, I started, my data come from 0.2 times and 0.5. And this is 0.169, 0.555. As I keep doing that, this is of course a trivial example, you will find exactly the solution, okay? The solution, you will find exactly the values. And therefore, it will realize, it will find what the function, the underlying function is. So this is how I'm skipping this. This is how the supervised machine learning works. This is a completely trivial example. I mean, it's instructional. However, this is how it works. When we go from this example to the more complicated things, we go to many neurons and many neurons. This is deep learning, usual learning. And these, of course, are ideas, as we also saw before, that come from the brain. But these are the basic tools. And historically, the first was the perceptron. And the perceptron, you see, has 3 inputs and has 3 W's, W0, W1, W2. We have to train the perceptron in order to match the input with the labels, the output, and in the process, we find these W's. Now, this works, as I showed you before, the same way it works here, the same way it works in deep neural networks, where we have many layers, many W's, millions, zillions, etc. ChatGPT works like that, everything works like that. So in the end, it's this type of algorithm and the search for finding the connections. We have even more sophisticated networks and so on. Okay, so this is basically how I'm trying to fix the idea of artificial intelligence, and in a sense, with one word, is searching for the W's, trying to find these W's, okay, the connections. Now, let's go to complex systems. Many of you, I'm sure you know that. Discrete breathers are basically like discrete solitons, intrinsic localized modes. There are modes that are very localized, but not because of disorder, because of nonlinearity. And this is an example of a discrete breather. And, we had this idea came in the late 80s. Many of us have worked on this, and I think it's a beautiful idea because it generates localization without disorder. Okay, now we have something more complicated, which are the chimera states, okay? And the chimera states, again, in discrete lattices in various types. They don't have to be Hamiltonian. You can sort of segregate the space, the real space, not the phase space. You can segregate in parts which are more regular and parts which are more stochastic, more chaotic. And this is a chimera. A chimera, from the ancient Greek thing, and I will show you. The thing means that it's a mixed thing. Okay. Now, I don't want to talk about abstract things. We are focusing on very specific things, and one of the interesting topics that also somehow connects now with quantum devices are the squid metamaterials or superconducting metamaterials. So squid is a wonderful device that's made out of basically Josephson junctions, and it has very interesting properties. I don't have all the time to go into this, but if you make a lattice of squids, okay, like I have here. This is a two-dimensional lattice. Each one of these is a squid. It's basically a superconducting ring interrupted by an insulator. Then in the sort of some zeroth order approximation, the whole lattice responds to an external driver through this equation. And you see this equation is very familiar, it's Newton with a sine term, non-linearity, has an additional quadratic in the Hamiltonian term, linear in the force. Okay, so this is an equation for the metamaterials. These metamaterials are very useful, and these types of metamaterials are also used as building blocks of quantum computers, okay, especially D-wave. Okay, now, you can do all the math and so on and so forth. You can find the linearized modes, but what is interesting is that in these metamaterials, we can get breathers, and we can also get chimeras, okay? So here is a one-dimensional metamaterial, and this is space, and this is time. And here we see basically the flux that passes through all these units. There are about 100 units here, okay? And what you see here, you see a part, and this is dynamics, you see a part which is quiescent, and this would be, let's say, the lion, because remember, chimera is a nonlinear superposition of lion, a goat, and a snake, okay? So here is the lion. Then we have the chaotic goat jumping around, this from Crete, okay? And this is periodic boundary conditions. Don't get confused that it's in the edge. This is a chimera. This is a chimera in a superconducting metamaterial. What is the chimera? It's a mixed state. Okay. Here's in the energy domain. Here's in the flux domain. It's a system that is spatio-temporally complex. Has some part which is regular, and this is a zoom in the regular part, and some part which is more stochastic, more chaotic. Could be worse than that. These are other chimeras here. These pictures were built by Ioanna Hitsanidi. So here you see a domain. So there are different chimeras, anyways, from these systems, and we can see a simulation that was made by Ioanna, and also I'll show you all three of them at the same time. This one-dimensional, two-dimensional, and you see some part which is going up and down, it's more regular, and some part which is stochastic. This is a spatio-temporally chaotic system. It's rather complicated, and it has a mixed domain, okay. And it's very interesting, of course. Okay, so let's go next. Okay, so I want to see if we can use machine learning to describe this kind of complicated stuff. Okay, can we use machine learning, the part of AI, to do this? Now, there are various methods, okay, and we heard before about reservoir computing. Okay, in reservoir computing, basically, it's like the ordinary thing, the perceptron that I told you, but additionally, you have a bath of nonlinear oscillators. So you have, if we were to think in Fourier domain, you have lots of additional frequencies to help you, okay, find things, okay. This is how it operates, okay, the reservoir, this reservoir layer, okay. Sorry. So we have reservoir, we have the standard feed forward, and then we have some more complicated things like this is called long short-term memory network, so LSTM. It's very famous because this is one of the, it's like one of the type of networks that also retains some local memory, okay, so it's useful. So what we did here in this work that I'm showing you, we actually used these three methods in order to investigate chimeras. Okay, remember, chimera is a spatio-temporally chaotic system. So let's focus on this plot. So here is a one-dimensional chimera, superconducting metamaterial. So you see one head of the chimera, the second head. So this is sort of the goat. This is more lion-like. And here's the space, and this is time. Okay, and we see the chimera propagating. It doesn't change very much, at least for this region, but it has some also internal structure. Now, what we do is we take these are numerical simulations. So we take the data and we train our three possible systems: reservoir, feed-forward, and LSTM. Okay. Now, training means, remember, I have input, output, and I have to find the W's. That's all it is. So we find the W's in the three different systems. Now, in order to do this, we need to use part of the data. So we need actually to use the data up to here for the two methods, which is the feed-forward and LSTM, and a little bit more actually the reservoir needs. Okay, and then after that, okay, we train the systems, we run them, and then we compare with the real data, real meaning the simulation. Okay, so now we compare it in, okay, let's see. We compare it at a given location as a function of time, and up there, okay, further up, in a given time location, but as a function of space. And the results are here. And what we see here, what you see there, the field color is the real data. Okay, it's the output of the simulation. And the lines that envelope are the three different methods. And what you see that both in space and in time, there's a pretty good match. Okay, so the lines above here that they sort of shape the whole thing are the results of the machine learning, and the full color is the real simulation. Now you see that there's a very good prediction of the methods, the three methods, more or less similar, both in space and time. Okay, so basically the first answer, the first result, if you want, is that, okay, if we train systems, then we can predict. Okay, we can predict a very complicated situation. Once we train, we can predict. However, there is a catch to this, and these are these arrows. Okay, now these arrows are very significant that I have there, because if I don't have these arrows, if I don't have additional input to the systems, then the predictability is practically zero. Okay, very little predictability. How do I get these results? By putting observers. That is, in the lattice of 256 units, I put periodically, this doesn't matter, I put observers. And so it's like sensors. So as I predict, as I try to predict, I have trained my systems, and then I try to use them to predict. However, by themselves, they go nuts. They go they don't know what to do really. But if I help them locally with sensors, then they can predict very well. So a similar idea, if you want, is, we have some sort of explosion somewhere in Piraeus, and there's a big, or better in Santorini, which is far away from here, and then a big wave tsunami goes to Crete. Okay. Now, if you want to predict this, okay, you need some information, but you also need some buoys on the way. These are the buoys. You need some sensors. If you don't have the sensors, this doesn't work. Okay, so we did this with this. There's another data set and so on and so forth. But these are the basic results here. Okay, so here I show you for the three methods. I show you the mean square error, the number of the percentage of observers, and the percentage of training over the total number of data I have. And you see in all three cases, the three different methods behave similarly, one better than a little bit better than the other. If I don't have observers, if I have few observers, the mean square error goes to, it's maximal. I cannot predict. Predictability increases as I put observers, and also I have to train. If I don't train, if I train very little, my predictability goes, nuts. Okay, so basically, in order to use these methods and they behave similarly, okay, I need I need training, but I also need additional things. It doesn't work just blindly. In the specific case, I need some additional information, okay, in order to be able to predict. Now, this is for chimeras, which is rather complicated. You can use similar ideas with other, for instance, with breathers. Breathers is a little bit simpler. Here is the work of an undergraduate student, and we try to see if we can compare, if we can detect, using, here we used CNNs, detect breathers versus phonons. Okay, now if somebody looks at this, it's very simple because breathers localize, phonons delocalize, so it's expected that he will be able to do that because we can also do this by just looking at it. Of course, it does this very well. However, the additional thing that it does, which is rather interesting, and it needs to be explored, is the fact that it can also recognize the breathers coming or the phonons coming from different potentials. So it has, we have three potentials here: the hard 5-4, Morse potential, double well, and then okay, it's not so visible, but doesn't matter. We have pretty high accuracy in detecting also which potential they are coming from. So in principle, you have a means, in this simpler case of the breathers, of recognizing that the breather comes from this potential, that potential, or if you want to go one step further, give me a breather, and then I'll try to find the, maybe I put a, 5-parameter potential. I try to find which potential is coming from. So there is a potential, that's another potential there, and I think it's rather interesting. Now let me close this part with the chaotic systems. I'm very excited about this, not because, I don't work so much with chaotic systems, but I think it's a very interesting application, connection of chaotic systems with autoencoders. So these are, of course, the famous attractors. And if I give you a time series, so all these are systems with three equations, okay? The first two, this is the Lorentz, this is the Rossler, the second is Lorentz, and then this is the other one, Lorentz 96, which has more equations, okay, it doesn't matter. I'm sure you know these are, of course, chaotic, and these chaotic attractors that have fractal dimension, etc. Okay, now, if somebody, let's say I have a system with three equations, like in pharmacology, for instance. Many times, like in the insulin problem, there are three equations. There are the two types of cells, the alpha and beta, and then there's another thing which I don't recall right now, but anyways, there are three equations. Okay, so imagine you have the three equations and you measure the amount of insulin in the blood. Okay, and this, imagine, is not really periodic, but it's stochastic, it's chaotic or something. Okay, but you don't know the number of equations. You don't know how big the space is. Okay, maybe you have three equations, maybe you have 23. How big is your space? How can you decipher that from only one time series? Okay, from the insulin percentage as a function of time. Okay, now there are very well-defined methods in the 80s, very clearly stated by Henry Abarbanel in his book in the 80s, 90s, I think it's 90s, and we try to find. We take the time series. We make delay coordinates, and then we try to embed this in space, and then there is some optimization. We try to find, okay, there's also some hand waving, and then we try to find what is the embedding dimension, how big is our space, okay? These are clear and well-defined, okay? However, I think we can do this with machine learning, and this is, I think, a very interesting, for me anyways, application of machine learning. Now, there is a beautiful construct in machine learning, which is called the autoencoder. Now, forget the chaotic. Not chaotic, it's really non-chaotic. So autoencoder has this symmetric triangular shape. So you have an input here, and you have an output. And you see, you have an input. I have a layer here, and then maybe I can put more layers, and then there is something in between, and then I have the symmetric part afterwards. Okay, so I feed in something, I shrink, and then I augment again in a symmetric way. This is called the autoencoder. The first part is the encoder, the second part is the decoder, and billion-dollar construct is this thing in the middle, which is called the latent space. So this does an information compression. Now, if I can make this three units here, if I can make it variable, okay, that is, I put 10, but I want to know what is the minimal number that is necessary, then I know how much information my data contain, and therefore I don't need to use more than that. So this information compression that takes place here can give me an idea of how much content the information again my data contain. Okay, so we use this with the three systems I told you, and our question was to use this as a variable. Okay, and it's easy to do this because we use something called regularization, technical, and find out how much information the data contain. Now we fed the three different systems. They go through this thing, and then we try to optimize and see how much information we need. Now, this is a busy plot. I just try to put everything together. Now, there are various superparameters here, hyperparameters, and so on. But basically, the bottom line here, this line here, so as a function of different parameters, it tells you how big is the space, how big is this latent space. Basically, it tells you that in the, and I'm sorry it's not very visible, in the Lorentz, like close to 3, in the other Rosslers a bit smaller, and in the other ones a little bit higher. Okay, and then you can also check about the exponents and stuff like that, so everything is kind of fits. And what we get from this is that we can get the information, how big is the system that this data comes from. Remember, I only give one of the time series, not the 3 or 23. I only give one. And it tells me how big is the latent space. It tells me, I give some mathematical function, I get physics. It tells me, oh, you need 5 variables, you need 3 variables, you need stuff like that. So the equation, so I think it's very nice. So this autoencoder works very well. Okay. And now, how much time do I have? Let us see. 10 minutes, okay. So I want to say, there's a famous equation, discrete nonlinear arithmetic equation. We know many things analytically in this equation. Okay, I have worked on this in small systems in the past. And since we know analytically many things, we try to test if we can get if we can discover the analytical aspects through machine learning. So this is one specific model within machine learning, within DNLS. This is called the targeted energy transfer model. This is from a paper we did with Serge Aubry and George Kopidakis more than 25 years ago. And now the idea here is that you have a donor and acceptor, and it's like sort of quantum or semi-classical, if you want. And so there's a barrier, and you want to tunnel from the bottom to the top or the top to the bottom. But there's also nonlinearity, and you want to optimize this transfer. Now, if there was no nonlinearity, the bigger the energy difference there is, there will be less probability going from one to the other because they are non-degenerate. The two levels don't talk to each other. There are two oscillators. But we have this energy difference, and we have nonlinearities in the donor and acceptor, and we want to optimize the nonlinearity with the non-degeneracy so that we have, if possible, perfect transfer. Now, we know the answer analytically because we did this 25 years ago, and we have the condition. So the question is, can we train the computer to do that? We have to introduce a loss function. It has to do with the maximum probability transfer. Okay, and we get, for the parameters that we have here, the energy difference 425 and the tunneling 1, we get, you see here, the parameters of the nonlinearity in the donor, 4.24, and the acceptor minus 4.25. This is what we get from machine learning. And then I can tell you the exact answer. We know this analytically. This is basically compatible. You see, this is donor minus acceptor equals the energy difference, 425 minus 425. So we can discover something that we know analytically by using machine learning and data. And this is good because this gives us confidence that we can discover, and we can go to cases that we cannot handle analytically. Okay, by the way, okay, this is how we do the search and so on and so forth. This is the optimal. We can, for instance, extend the system into a trimer. Now, this is non-integrable, it's chaotic. Now, what is the optimal nonlinearity in order to be able to do this optimal transfer? We cannot solve this, okay, but machine learning can, okay, and we can find basically two minima which give us the values. It's either this or this. This is the deepest minimum, and this will give us the optimal transfer. So this is a good way, I think, to use machine learning. First of all, make sure that it works, and then extend it. Okay. So now we can do this quantum, etc. Now, can we predict the future? In order to predict the future, I think we need data and equations. And this is what Klaus Meissner mentioned on Friday, that we have to embed also equations. We made this up, this is called physics-informed machine learning. We use this in order to predict the sort of the evolution of COVID in several countries, and in particular Greece, that I have here. Now, how did we do this? We were every Friday we would get the data that were available, okay, from which are the infected people and so on, okay, and we also had this model. This is the SIR model, which connects susceptible, infected, and recovered that don't have to be there. We do a little bit of math. So we have data and equations, data and model. And we connected these two by making a loss function that involves both the data but also the equations. This is a standard approach. Karniadakis sort of introduced this, and I would say these ideas come from Akis Zagaris, from Ioannina, which he did this kind of stuff like in the beginning of the 2000s. And here's the answer. Okay, so basically the green are the data that we get from the the official data, and these are our predictions. And basically the predictions take the data, fit it to this model, the SIR model, and then use the model for predictions. Basically what you see, and the predictions of course are, we have the data from the previous week, and now we compare the data with the predictions. Okay, some cases they work, some cases don't work. Here was a lockdown, we lost it, but then it sort of recovered. So basically, if you combine data with equations, as Meissner also mentioned on Friday, I think you have a possibility of predictability. So let me mention a little bit medical applications. We have been working with cardiologists, and the issue in the heart is to connect the propagation of the wave in the heart with observations, which is ECG. And we took data, we digitized everything. We took the ECG and turned it into parameters. And we have a number of things that I want to mention. Now, this paper here that I'm presenting basically shows that if you do this analysis and you use machine learning, simple versus machine learning, trees and forests, then you can actually, with this data, you can predict the hypertension, okay? Which is not an obvious thing to start with. However, a sort of judicious application of machine learning can actually take you in directions that you would not expect. Now, what you want is you want some physics also. Physics was also This is the model of Hodgkin-Huxley applied to the heart. This is a complicated system. Now we can solve this. We can get various results. Okay, and connect the dynamics with the ECG. Okay, and let me just show you some pictures. Show you these pictures. Okay, this is in 2 dimensions. So we have propagation around it. So imagine the wave in the heart, starts from the upper part, wants to propagate, and there is some ischemia somewhere. Okay, there is a defect in terms of physics. What happens to this wave? Okay, so let me show you what happens to this wave. So in the center, we have an ischemic situation. The first one is healthy. The second, this ischemic thing is very shallow. Then it's larger, and then it's larger. Okay, which basically shows you how, as the wave propagates, part of this energy, if you want, of the electrical wave is trapped in this defect in the heart. Okay, now this is very useful information, in my opinion, because if I can now couple this, we have not done this. If I can couple this information to the data, okay, of specific data from hearts that have this kind of behavior, then I can basically predict what will happen and what is the global behavior of the heart. So I think the combination of machine learning with physical modeling can give information also in very complicated things like medicine and heart medicine. Okay, so let me close with almost close, so another 5 minutes, okay, or less. So we want to embed quantum in this picture. So let me skip this. And we want to make medicine quantum. Okay, everything's quantum, but we want to do quantum. And this is an example where we took exactly the analysis, hypertension analysis that we did with classical means, and we did it with quantum. Now, why do we do this? Okay. Now, there's absolutely no reason, okay, except because we know as we want to do certain. However, if you have very little data in medicine, there's no problem. You can do everything with classical computers. But the data in medicine increase, and increase exponentially, maybe even super exponentially. I don't know. Now, soon we will not be able to handle this. Maybe we are not handling this, so we'll have to use quantum. Okay. So here, I'm saying, I'm not talking about today, I'm talking about some days from now, some years from now, where the amount of information is so big and the presence of quantum computers is so dominant that we have to do the analysis in quantum computers and quantum techniques. Does this give us anything better? Does this give us anything good? Okay, so this is the problem that we know. We know the solution because we analyzed it. So now, what we do, we have 6 features out of all these 30 or so features. We actually, the most important one is 6. So we take the 6 features, okay, and we embed them in the block sphere. And we need for each, we need 3 block spheres. Because in this block sphere we have 2 angles. It's a unit sphere with 2 angles. So each one of these 2 numbers, the 2 angles, is associated with 2 of these features. Okay. So then we take this and then we put it in the quantum computer. Okay, we write a quantum code in the simulator. Okay, we tried it also with the IBM, and then we want to ask the same question as before: can we detect hypertension, but now using quantum techniques? If you want, if you don't like the sound of it, maybe let's assume that we go to the Fourier domain. We have some data in real space and we go to another space, Fourier domain. So we do it in another domain. It is good enough. That's all. That's the only thing I'm asking. And so here's the answer. Okay, this is we just uploaded this in the archive. So if we do the classical method that we have already done, we get basically an efficiency, let's say, cross validation 74%, and with quantum we get 71%. Okay, so we lose a little bit, but not dramatically. These are very few data. So the basic result with this method, the specifics method, shows that there's no supremacy, for sure. However, we are not very far, okay, from matching the classical. So therefore, if I have this amount of data, it's not worth it doing it quantum mechanical, but if I have a huge number of data, then I should be able to do it. Now, the autoencoder can go even further. It can be used in quantum mechanics. It can be used in the context, in the quantum context, where it can also try to answer whether there is some latent variables in the problem. So I don't have time to go into this detail. This is, I think, an interesting new thing, but if somebody wants, I can answer. Okay, so let me close. Look, I was very technical. You allow me 2 to 3 minutes of philosophy. Okay, so in my opinion, the first data scientist was Thalys of Miletus for 2 reasons. One, because he predicted the solar eclipse of 585, and the second, he predicted the weather, a long-term prediction, and he actually made money out of it. So my favorite quote here is Aristotle. Thalys, so the story goes, because of his poverty, was taunted with the uselessness of philosophy or physics or whatever, but from his knowledge of astronomy, physics, he had observed, while it was still winter, that there was going to be a large crop of olives. So he raised a small sum of money and paid round deposits for the whole of the olive presses of Miletus and Chios, I don't know where else, which he hired at a low rate, as nobody was running him up. And when the season arrived, there was a sudden demand for a number of presses at the same time, and by letting them out on what terms he liked, he realized a large sum of money. So proving that it is easy for philosophers to be rich if they choose, but this is not what they care about. I'm sorry, I have to show you, this is my favorite quote from Aristotle. So the future, I think, is interesting. We have to do digital twins, and digital twins will help us work in the cities, in the whole world, because it will be like an extension of simulations. And of course, we will have to compete with GPT and other stuff. How do we compete? Okay, so natural intelligence, 250, so the cats. Dogs actually are twice as intelligent. 250 million neurons, billions of synapses. W is the important thing. Humans, 100 trillion synapses. GPT 3.5, 175 billion of parameters. W's, okay. ChatGPT 4 of the order of 2 trillion of parameters. So they are closer, okay. I should be afraid, okay. Now let me compare an LLM with a child. So the internet data volume is of the order of 10 to the 13 bytes. Okay. So now let's see. If I have a human that reads 8 hours a day and reads 250 words a minute, okay, then 8 times 60, 250. Okay, this is to turn it into tokens. Okay, it doesn't matter. One person, each one of us, can read, let's say, megabyte per day. Okay, now if you divide 10 to the 13 bytes by this 10 to the 5, in order to read all internet, you need 170,000 years. Okay, a long time. Okay, but there is vision. Okay, now in each one of our eyes, there are these bundles, fibers that come in, and each one of them has about 1 million fibers. And each fiber, okay, carries about 10 bytes per second. Okay. So with the 2 eyes, we can get 2 times 10 to the 7 bytes per second. Okay, so now if you take a 4-year-old child with approximately 10 wake hours a day, he or she has 16,000 hours in the first 4 years of life. So this is the first 4 years of life. It's 10 to the 15. This is 10 to the 13. So a 4-year-old child has seen 2 orders of magnitude, more or less, more data than the LLM in his first years of life. So the comparison with LLMs, and all the other stuff, should be proper, because we have an edge here, at least for now, and the edge is vision. and all of you, I'm sure you have played with ChatGPT. It's abysmal when it comes to pictures and so on. It gets better, however, it cannot handle that. Okay. So, of course, we are in this era of AI. They stand on big, strong shoulders of statistical mechanics, spin glasses. They got the Nobel Prize 2 years ago. But also don't forget the chemistry prize, because this is and also related also to pharmacology, to pharmacy, because they are in this kind of department. They managed to solve one of the fundamental problems of protein folding problem. Complexity is a common language. AI can uncover low-dimensional structure hidden within high-dimensional data. Physics and machine learning share a common goal: discover the essential variables. Medicine provides a natural domain. Quantum learning represents an emerging frontier that I think is quite interesting. Let me advertise my book, where some of the things you can find, and I thank you very much.
Is there a question? If not,
There's a question. I'm not familiar with this technology, but let me explain this layer things. Yeah, it's very okay. Basically, right? I understand. Okay. So look, if I have, so imagine that I have a transformation matrix. I have an input, and I have a linear matrix. Okay, multiply the input, I get the output. Okay, this is completely linear system with visual stuff. Now imagine as I do this as this transformation, there's also something non-linear in it. Okay, so I have this linear matrix, and I have something non-linear, and I will have to put it somehow, and then maybe another linear thing. So I have a pipeline that is linear, non-linear, linear, non-linear, linear, non-linear. Okay. Now the non-linear, at least in all these examples, the standard is fixed. There's some non-linearity, you don't play the parameters. There are some ideas on that, but people, 99.9% don't do that. So we fix the non-linear layers, and we try to discover the linear matrices, which could be 1 or 2 or 10,000, 10 million. Doesn't matter. So if I put many layers, okay, then I have non-linear elements, fixed, frozen, and I have the linear elements that I have to discover. So I have parameter A, alpha, 1, 1. So these are the W1, W1, etc. Okay. So in order to discover this, I have to do this process of learning. How do I do this? I match the input with the output. The output is the label. So this is so a stone is falling. Okay, we know the height and the time. So the height and the time are the input and the output. Okay, or something else, much more complicated. Now, by putting lots of stones and lots of data and optimizing, I find this W, I find this linear path, and that's it. Once I have this, this is it. So I take it in my pocket, okay, and I say now this system that I have created mimics the specific system, okay, within reason, okay. It fails here, it's very good there, and so on. So this is the art now of making this work. But the idea is this, and this idea is not new. I mean, like it's from the 40s, percent of the 50s. So the layers are the non-linearities, for example. The non-linearities are usually fixed. They usually have them in the beginning, or like hyperbolic series. They need to have a threshold. Okay. So usually there's hyperbolic series, and then something, some other simple functions or so on. But these are usually fixed.
I have a question about how to validate the extension of the machine learning model from a system that you have used for training of this model to other systems. You presented an example of driven extension of the machine learning model. How do you know the machine learning model to develop what other systems can be used for making predictions?
Yeah. I mean, of course, it's a $1 question, right? I mean, maybe more than
It's a question. How do you know the machine learning that is trained for a specific set of data that should be extended?
Yeah. Okay, so that's why, okay, I pass it very fast. So I know how to solve some problems analytically. So I believe in analytics. I don't believe in, let's say, Wolfram's cellular automata and stuff like that. I want to see functions. Okay. Now, if I see function, I feel good. All right. So I take a system where I know how to solve analytically. Then I train with this data. I train a machine learning system, and I see that it works fine. Okay. Now I extend this to the case which I don't know. Okay. Okay. I mean, it's not obvious. However, it's not unobvious also that it will not work. So I see this procedure in some sense like perturbation theory. Remember, when we know how to solve a problem analytically, we go and we have a point, and then we start looking around in the area. Okay, I don't necessarily need the theory because I have the theory, but I look in the area, and I think this is this is the confidence. On the other hand, if you want more mathematically, which is not my my interest. We know, as was mentioned before, that there are famous approximation theorems. I mean, we know that neural networks, if you have a long enough neural network, is a perfect approximation. Okay, so therefore, I'm happy because I know there is foundation in this. Okay, now I don't know how long, maybe infinite. Okay, I'm not going to go that far, but I can play with.
Thank you very much. If there are no other questions, let's thank the speaker again.
So then we're going to pass to the first speaker of the session, which is Professor Sopos, who is going to present physics-informed neural networks and support integration as experience with AI subjects and full-bound terminals.
Thank you. Okay. Well, my talk today will be about physics-informed neural networks. We've had some of them in the previous discussion. Along with symbolic regression, the second method we use them as explainable AI surrogates in wall-bounded turbulence. So, turbulence is something that matters because, for example, we have more than 50% of commercial aircraft fuel consumption linked to turbulence. This and another phenomena of our daily life really matter and we have tried a lot of mathematical models to solve them. And how does this connect in chaos and complexity? For example, turbulence is chaotic. It's sensitive to initial conditions. That means that even with a small perturbation, something bigger might happen. But it's not totally random. It's governed by deterministic equations, such as the Navier-Stokes equations. It contains a multi-scale complexity, for example. In turbulence, in fluid flows, we have energy cascades from large eddies. The kinetic energy is high there. And these large eddies tear down to small vortices until they reach the Kolmogorov microscale. The scale separation grows as the Reynolds number increases, and that means that we cannot have high fidelity simulations here because the cost becomes prohibitive. However, despite chaotic fluctuations, time average profiles will help us here. We have the chaos averaged in predictable statistical structures. If we want to simulate such systems, we can use various methods. The scale is that we start from runs, which is the industry standard. It's very good in accuracy, and the computational cost is rather small. As we go upper this pyramid, we arrive to direct numerical simulations. This is something that is very demanding in terms of cost and complexity, and we cannot always perform simulations like this. But if we can, then we're in front of very high quality data to use and train our machine learning models. Here we have a three-zone model. That's a very famous model in fluid dynamics. I will stand mainly on the blue line. This is the logarithmic layer of the velocity profile in the channel. The logarithmic layer is somewhere inside the viscous sublayer and the turbulent regions, where we start having the turbulence. And two main parameters characterize this. This is the K, the von Karman constant, and the parameter B. These are constants that we want to find their exact value because this changes. It has a central lobe here in turbulence, the von Karman constant. It's commonly reported as about 0.41, but it's not the standard value because we have found that this changes and we have to adapt it in our system. To have a comparison baseline, we chose 4 semi-empirical theoretical models from 1979 to 2018. These are the most famous fully explicit equations. We have more of them. Each term inside them, like the arctan term or the log term, describes a different part of the velocity profile with the same accuracy. As we move from 1979 to 2018, we get better models. But as you can see, they are somehow complex. They're not very easy to use. So, to start with our survey for this, we have used DNS data. This is the ground truth. This is the most high-resolution output we can have. Experiments are not very popular in terms of giving us many data to train the models. So the DNS data that we found come from 15 different cases. The computational cost goes fast, so we get a number of around 10,000 in Reynolds, friction Reynolds number, which is very high. We did not find something bigger than this in the literature. We're expecting some results around 16,000 from Japan research team. And we introduced the Reynolds, the friction Reynolds number with the Greek tau here, which is somehow different from the standard Reynolds number because it depends on the friction imposed down at the wall. While the standard Reynolds number is a more average quantity that takes average quantities in mind. Our framework here uses both physics-informed neural networks and symbolic regression. With pins, we embed the governing equation in the loss function, as we saw before. We learn the physically meaningful parameters that we want, and we can also extrapolate to unseen Reynolds number with high accuracy. We'll see how it's done. While with symbolic regression, with genetic programming methods, we get the full white box method, which is human-readable since it extracts analytical expressions. And we see that it improves at higher Reynolds numbers, which it's something that it's a bit tricky. It's better because we have more data in higher Reynolds numbers, so we have a richer database, and so we train our model better with this. The PIN approaches we use are two. The first one is the K epsilon turbulence model plus the log log that we saw before. This is an approach that we don't take account of any training data. We just solve the equations with pins. And we get optimized constants for all the parameters of interest. And we get a very good error reduction here. And in the second framework, we train our PIN with real data. It's DNS trained. It's different than the first one. And here we also enrich the loss function with some theory, for example, the one traced near wall dubbing. And we get also very good results, as we will see next. The first one is the PIN with the optimized inputs. We optimize the parameters K and B, and we then feed to the network. The loss function integrates both data fidelity, governing equation residuals, and boundary condition domains. We have to give the constraints of the boundary. And so we enforce physics here. From a least square analysis, we get the values of kappa and B. We choose a rational law. And we see that K is not a universal constant. It varies across all the Reynolds number that we have. And as we see in the results, we get less error and better consistency with the DNS results, especially in the higher Reynolds numbers, which are more demanding to get results from there. This also applies to the second order parameters like the kinetic energy. This is something that the error propagates here, so we also get less error than the standard method here with the pins. And if we compare the computational cost, then we get very high advantage. For example, for a simulation that we need above 160 hours, now in less than 24 hours, we get our result with less error. We're getting closer to DNS. The second network that we used for pins also gives very good results. I have some examples here of various Reynolds numbers. But the fact here that I want to stay is that in this framework, we have used all Reynolds numbers until 401.79 as the training data and left the larger Reynolds number outside the training. We extrapolated the method to get our values for these three higher Reynolds number. And we see that as we imposed all the physical constraints inside the models, we get good results even for cases that were unseen. And that's something that's very promising. If we leave pins aside and go to our second method, this is the symbolic regression. Here we perform an evolutionary research for the mathematical expression that best fits the data. It's a purely data-driven method. It has no physics, but it approaches physics as it goes on. For example, from a random population of math expressions, we get, through some genetic operations, we get the best analytical formula for the data that we are dealing with. So in turbulence here, we discover scaling laws automatically from data. We get fully interpretable expressions, and we can confirm or challenge the classical theory with this. For example, in comparison to the previous semi-empirical equations I showed before, we get various analytical equations. We have to check which is best and fits our problem. For example, here we have a three-term equation with various alpha parameters. The first one replaces the linear sublayer. It means that near the wall, it captures the behavior of the phenomenon. We have a second term that approaches the log layer structure, and the final term that goes to the outer region. And this equation outperforms the 4 other models that we have in the literature. To go one step further, we took the indicator function C, which is the first derivative of velocity, in order to weight the changes that might happen in the profile. So, through this derivation, small features from velocity become visible here. They are clearly visible. For example, if you see the max value here for the indication function, then there are changes that were not visible in the velocity profile. We want to reach the plateau. The dashed line here is 1 over kappa. It's 2.44, the most frequent value of kappa from the literature. And we want to get a plateau after some y plus there to be consistent with the theory. You can see that, especially at small Reynolds number, we cannot distinguish between the DNS data and the pins. As we go to the higher Reynolds numbers, we can see that there are some fluctuations here, but mainly the pins seem to fully address the problem here with the DNS data and the indicator factor. The symbolic regression, on the other hand, gives us as well a new analytical equation for Xi. It's a universal single formula that applies for all Reynolds, frictional Reynolds number cases. The exponential term drives the buffer rise and the peak that we saw. The hyperbolic tan captures the log layer plateau, and the constant is the viscous offset. And we see here, this is what the SR algorithm has given us. The results here are better for smaller Reynolds number. We have some differences here with the DNS, small differences. It does not work like pins, but and if we extract some metrics here between them, the pins and the symbolic regression, we have larger errors for symbolic regression, but these errors become smaller as we increase in Reynolds number. That does not mean that we can choose one of them as better than the other. They can work together. For example, the pink strengths are the lower error. The accurate extrapolation, even to higher regions of the Reynolds number, and it can learn physically meaningful parameters for our models. The SR strength is is that it's fully interpretable. We have a closed form equation that we can understand and mathematically explain what it shows us. There are no black box weights, it's fully auditable, and it reveals hidden scaling laws automatically. Together, we can use pins for precision, symbolic regression for explainability. They can work complementary here in turbulence. Both surpass all classical profile models, and both are orders of magnitude faster than DNS. That seems that we can bridge classical fluid mechanics here with modern machine learning grounded in DNS data. And taking all this into account, we can see that each one of them, pins and symbolic regression, offer distinct strengths. We introduced the indicator factor, which is also a powerful diagnostic for this. And we can see that we can create a complementary framework for both to work. But this does not end here. We have much work to do, for example, to extend from such planar channel flows to pipe flows or curved channels or more complex configurations for this. And we can embed the functions that we learn, for example, the von-Karman constant depending on Reynolds number. This can be directly added inside the known runs solvers for production, for real industrial production of CFD. That was all. I think we are okay with the time. Thank you.
Thank you, Speaker, for this talk. Are there any questions? Yes?
Yeah, and I say that you found the symbolic expression using a generic algorithm.
Yes.
This is very common sometimes. Can you say something about how many epochs did you consider? How large was your?
It's not we used. Yes, I understand the question. It's a main question I hear many times. The genetic programming here that we used, we start from a different random state every time, and we get a bunch of equations. We talk about hundreds of equations here. So the fact here is that we have to be very careful to choose the right one, because in terms of just data loss, many equations may be good, but they do not apply to the physical problem. So we have to know the physical problem previously. We have to have knowledge about it and select those that comply with physics. That's why I showed before the semi-empirical models, which is a direction of what to choose. For example, do we have a log term here? The log term explains something in the profile. Do we have an arctan term? So it's more like an optimization problem then. We have the terms and we optimize the variables and the constants that are inside these bunch of equations. Okay.
Interpretability is the outcome of the fact that inform the system produces the physics we have.
Yes.
Only for that.
Not only for that, it's just because we have an analytical expression. So if it's analytical, then someone might explain it, interpret it. So it depends on if we know the problem, then we can interpret it to others that it follows physics laws. It's not something that.
If you don't know the problem,
If you don't know the problem, you just you don't know. You guess. I don't know. It's better.
if I don't know the problem, this interpretability is questionable.
Yes, this is why we try to bind it with physics. So if we know the physical problem, then we know how to move. If we're just computer scientists that want to present an algorithm, then it's most probably we don't know how to explain it because it's not our case. That's something that the physicists should deal with because they have the knowledge and they can explain it.
If I can intervene, I think there is also the problem of what you mean interpretability, because one thing is that this second methodology is not a black box, so you can diverge. Because in terms of interpretability, if you want, for example, to find a trend or something, perhaps you can find also with other methods. But it's just a trend, you don't know what is the function. Here you have also, I think, the function which you can see if it behaves normally within physics. Even if you don't know exact physics, for example, you have something, a gas, and you heat it, you expect that the pressure will grow. Perhaps you don't know how it will grow, so you can have a tendency the model represents well the trends, I think. So you can interpret and you can have the ratios. But in other cases, I think you can have also some interpretability, for example, an increasing variable is increasing another variable, but you may not have an analytical relation with another method. Sorry for the interruption. But yes, I think we have some time because yes, but yes, we will have some time. Yeah.
My question first, the concept of interpretable AI appears as a requirement for the black box approach is somehow not accepted. So even the European Union is putting interpretability as a requirement. Now, my question is, interpretability here is not intrinsic, but it is somehow inserted by giving physical information. That is what I think.
It depends to me. It depends more because there are two methods here. It depends.
What's qualification?
Where you give the equations and there is the sub, there is a qualification where you take equation. You don't give equations as qualification. It's a medical algorithm that uses, if I'm not mistaken.
Yes, but we can add constraints of physical importance to the symbolic regression if we know them. If we know, yes, we can add them as well.
It's something we can discuss it, and there was somebody else. So, somebody.
My question is in the same context. How easy is to identify the physical significance of its term in a form of extraction qualification?
The physical significance emerges from the first question I answered. It's because since we use random starting points for our algorithm, and we use it, for example, for 100 times, if we see in the output, then it means that something happens there. This is the first indication that these terms enclose some physics.
Okay, and are you using this physics inclusion in the evaluation of your formula? Because from support relation, you get a lot of plethora of formula. And then you evaluate their simplicity, and you are making your choices. Do you take into account the easiness of the physical interpretation of formula?
If we have one, yes. But in cases we cannot have, we do not have. We may have astronomical data, for example, where we don't know if there's something that captures their behavior. So we cannot add anything there. If we know, then it's easier. For example, in fluid dynamics, we know some things. We expect some things. So we expect them to appear. That's a validation that our method works. Something like this.
Practice makes qualification in data, you know, the background physics.
Yes, yes. That's something I believe must happen.
Is there any other question? Okay, so we can finish with you again.
Next and last.
Next and
Last.
Last but not least,
Okay.
represent multitask convolutional approach for structural characterization of complex
Okay, thank you very much. Actually, I made the title a little more general because we have some time. We are moving to another field focusing on spatial domain and mainly on the spatial domain of nanostructured materials, on what is happening on material surfaces or material bulks when we are able to create, in a controlled way, nanostructures. We know during the last decade that nanostructuring surfaces and materials is very effective in order to multiply the functionality of materials and to push a new generation of applications, okay, in many areas. I will show some examples in the slides below. Our focus is to understand better, or to try to understand better, the geometrical, the mathematical description of nanostructured materials. Actually, I will, okay, this is some acknowledgement. This work has been done with a lot of colleagues, students and colleagues, and has been funded by some projects. The outline, first I will start with some motivation and the context, taking into account yesterday's discussion with Theodoros, an enthusiastic discussion, lively and lovely. Some clarifications and to focus. I will focus on two aspects. The first is about the complexity of surfaces on nanoscale and how we can deal with it, how we can talk with it. I will present some concepts inspired by chaos and entropy for their characterization, and then I will move to the talk about Moiré systems and membranes. And first, the AI explorations of their properties. The motivation is shown in this transparency by this collection of, just a moment. Oh, this is for, okay. Is it work? Έχει φαίνεται πιο. Δεν το ξέρω αυτό, είναι ένα φανταστικό. Οκ. No. It's shown here. In this transparency, I present some images taken from microscopes, from scanning electron microscopes or atomic force microscope, which show surfaces of materials. As you can see, there are a plethora of nanostructured morphologies. And you know that in nanotechnology, the two main pillars are our ability to nanofabricate, the first one, and the second one, our ability to measure the nanostructures by using mainly microscopes, but also a lot of other techniques. But the output of this, in many cases, is what we call nanostochasticity, which means that, I will show it below, that we don't have, in many cases, like this one, structures like this one, in which the nanostructures are well arranged on a specific grid, but we have some randomness or some stochasticity, or in more technical terminology, the roughness of the surface. We're interested in the characterization of stochasticity of nanostructural morphology because it penetrates almost all the chain of nanotechnology, from fabrication to the property and use of nanoproducts. Most nanofabrication techniques, both bottom-up and also top-down, create structures with stochasticity. Also, stochasticity should be considered when we are trying to measure and to characterize in a quantitative way these surfaces. And also nanostructure properties and functionalities are very sensitive to the details of this stochasticity, which is very critical in applications of nanotechnology. And this is an example. You know that when we have a surface, by tuning the chemistry of the surface, we can make this surface hydrophobic. But when we combine this hydrophobicity with a properly defined roughness, then we can take superhydrophobic surfaces in which the droplet behaves such like a solid, almost solid sphere. And this is very useful in a large variety of applications. And the challenge of, yes? Nano or micro. Okay. Not on this, but the nanostructures are here inside this. Okay. This is this structure here. This structure here. This is the step here. But these surfaces are nanostructures. Okay. Here we cannot see the nanostructure because we focus on the droplets. The droplets are at micrometer scale. Okay, so the challenge of nanostochasticity is to find the proper mathematical and computational methods to characterize this. Before going to focus on complexity and more membranes, I should make two clarifications. The first clarification concerns the relationship between surfaces and images. We're talking about the complexity or the nanostochasticity of surfaces, but what I show you are microscope images or microscope measurements or microscope micrographs of these surfaces, of these structures. And the question is are these images representative or validated to be used for the quantification of the properties of the surfaces? The answer should be based on the following, on this formula here, that is the image is actually a combination of the convolution of the measurement process with a real surface. The measurement process usually is the effect of using a probe, electron beam, or a tip in AFM measurement, and the detector for translating the probe reactions to the measurement image. So the assumption is that the parameters characterizing the image, the microscope output of our measurement, are related with the parameters of the surface, but should be quite cautious on this relationship and to put always the question in order to be sure that this correspondence is true. There are many cases like this one in AFM image. You can see here. Okay, in this case here, you can see that we have the real protrusion, the AFM tip. Since the AFM tip is much larger than the protrusion or the similar scale, the output of the measurement is wider than the real protrusion. So we should be aware of the restrictions, of the limitations of our microscopy in order to evaluate this correspondence. The second question is, what is a surface? The second clarification. It is not a very easy question. It depends on the point of view. The more conventional way is to answer, to say that a surface is actually the collection of surface atoms. Okay, this is the first a realistic, solid state-based approach. The second is to include in this consideration also the surface roughness, and to say that, okay, what is surface roughness? Surface roughness is the deviation from flatness or from smoothness, a more geometrical meaning. Due to the large functionality realized during the last years of the rough surfaces, we are moving to the next interpretations of what is a surface. A surface can be considered as the information channel of a material in its communication with environment. But it is a different approach, a different meaning of what is a surface. And the surface roughness, that is the surface morphology, is actually the language that this communication channel is using in order to transmit messages from the material to the environment and vice versa. Okay, this is the basis of the metrics we will explore in the next slide. So the first is to identify, to define the complexity of surface roughness and to make clear what is the difference from the stochasticity or from randomness. When we have here the whole, okay, it's very nice. When we have this chain from the fully organized surface with no fully symmetrical, with no randomness, to the fully randomness surface, we can have a whole sequence of controlled randomness. If we are using measures for randomness, then the randomness is going to be increased from this extreme to the other extreme. but we have found that the most useful surfaces and more functional ones lie in between here. So the challenge of complexity approach is to find metrics which are maximized between fully symmetrical and fully organized structures and fully random surfaces. So we'll present very briefly two ideas. The first is to use the multi-scale Shannon entropy in order to define the complexity of surface. And the second one is to use a virtual dynamics of surface, that is to bring together our knowledge from chaotic dynamics to image analysis, okay, in order to understand the complexity of images and surfaces. So the concept is here we have surfaces and we want to find the metric to be maximized between the smoothness and the fully randomness. So the concept is to start with initial image, with initial structure, and then by smoothing gradually this structure to degrade the information it conveys. Okay, so we apply this smoothing transformation, and we are diminishing the structure after some application of this transformation. And we measure at each step the Shannon entropy, that is the information that this process has. If we have, this is the first approach, and it is can be implemented in 3 steps. I will not go in details, but I will present this one. This is, I think, the most explainable diagram. If we plot the entropy versus scale, and we have a fully random scenario, a fully random surface, then very usually, very fastly, we will lose the information we have on our surface. That is, after some steps of smoothing, the information will be minimized. And so the entropy goes to 0 very fast. If there are some periodicity, we have some oscillations. But if we have surfaces with structural heterogeneities which persist in scales, that is, we have a rich structure, then this curve will remain at high values. So if we define the complexity as the sum of these values, this means that in the complex appearances of surfaces, then we have high maximum complexity. And indeed, if we measure, and I will show some examples below, if we measure the complexity of such surfaces, this metric is maximized in between the fully organized and the fully random cases. So the surface complexity can be approached as the structural heterogeneity that appears in multiple scales. So we have information enclosed in multiple scales. And we have justified this idea, and we have generated a lot of synthesized surfaces with controlled complexity, and we have identified that this scenario indeed presents some maximum between the noisy and the smooth cases, and also here the same conclusion. And also we have applied this approach in real SEM images from surfaces coming from the etching of some chlorium, copper chlorium, and chlorium iron chlorium, trichloride iron. And we have seen that in these cases there is a difference between the entropy versus scale curve and the total complexity. This surface here is more complex than the second one. And this difference can be matched with a difference of the experimental evaluation of these surfaces concerning the heat transfer that present. okay, in water condensation experiments. So we have some first results that this complexity has some relationship with the functionality. Now, the second approach, more explorative and more strange, is to use the chaos in order to, again, to find them, to propose, to develop a metric, a methodology, which characterizes the surfaces in order to find the more complex ones. In this case, the comparison will not be done by the smoothing process, but by a noising process, a mixing process. Actually, we take the initial image, and then we apply on this initial image a chaotic transformation. In this case, the Arnold cut transformation, in order to mix the pixels of the image. That is, the dynamical state of the image is the collection of its pixels, and we change the positions of the pixels following the specific chaotic Arnold cut map. You know that in the Arnold cut map, that's going to this image here, when you have the initial cut, after some iterations of this transformation, chaotic transformation, we have a disappearance of a damage of the initial structure. And the idea is, by following and by quantifying this damage, this destroying transformation, how we can identify and quantify the complexity of the initial image. If the initial image is resistant to this process and preserves the information during this destroying transformation, then we evaluate its complexity as very high. Okay, similar concept, but different implementation with the previous approach. And actually, we apply the two basic concepts of chaos, the stretching and the folding of the phase space in the chaotic transformation, and we apply it as the image, and we quantify their combination with a Fourier analysis at the last step. And this point is also, we have applied it in a lot of simulated surfaces, and we have found quite reasonable results, and this was the basis in order to move to experimental images, because our laboratory is mainly an experimental and application-driven laboratory, so our theoretical concepts and methods should be tested and matured in real experimental cases. And we have found that indeed, when we etch by hydrochloric acid aluminum surfaces, then the surface is becoming very complex, and this is used in many applications. And we have found that indeed this complexity metric is maximized at the etching time at which the surface is more functional in the specific application we study. So let's move to the Moiré membranes, as George Cironi said in his talk. Moiré membranes or Moiré patterns is what we mean by Moiré patterns. Moiré patterns appear when two or more periodic grains with hexagonal symmetry in most cases are overlaid, are stacked one upon the other, and are rotated, okay? And this creates a new, larger, complicated patterns. We can put two, here you can see the patterns that we can create, we can get by simply rotating two Moiré pattern, two grains. If we put more grains and we start to rotate this, we can imagine how rich are the structures we can get. So the applications, the best application, the most famous application is twistronics. That is, by rotating these grids, we can move from insulator to superconducting cases, and this is a new era, a new area in nanoelectronics called twistronics. And also, we have found that in larger scales, this rotation, these patterns can be used and can maximize the water condensation phenomena, and so it can be used in membranes. And also we have, during last 5 years, we have a lot of publications on 3D moire materials. Here, we started to play and to see how AI can be used in order to understand and to make some predictions and some measurements in the case of these complex materials. And the question we posed is how we can, by looking at the pattern, at the moire pattern, how we can find the number of layers that I have stacked in order to create this pattern. And the second, what is the width of the links in this pattern. And so we have developed a dual task convolutional neural network. We take as input images from the input patterns. We transform this to black and white, but it is not needed. And we can predict, by training this model in synthetic data, we can use this model then to predict the number of the superimposed layers, first, which is a classification problem, and the second is a regression problem, that is to calculate, to extract the lattice width prediction. The interest from a machine learning point of view is to this dual task, that is to combine a classification with regression problem. And actually, this work has been done in order to get more experience on using dual or multitask convolutional neural networks. And we have found that the success is quite high. So we have satisfactory F1 scores in predicting the classes, the number of layers, of superimposed layers. And also, when we are moving to the regression with prediction, again, the R-square is quite, this is the first results, are quite promising. It's close to 0.97. So we have applied this in test samples, and we have made systematic calculations, application of this machine learning model in order to calculate the width in a dynamic way. This is very fast. And and the conclusions from the first focus, from the challenge of nanostochasticity, the first is that when we change the context of studying nanosurfaces and nano-structured materials, then we can be inspired by information and complexity concepts such as chaos and multiscale Shannon entropy in order to quantify the enclosed information in an image, considering that this quantification is quite critical in the functionality of the surfaces. And of course, we can use both metrics in order to quantify the complexity of any image, and we have made some work on this. And in the second focus, the challenge has been to make, in some case, inverse engineering, that is to predict, to put as input the output, that is the final moire pattern, and to predict what is the number of layers we have used in order to get this pattern, and to the width of the standard width, the similar width of the links of the patterns. Okay, this is the first result. We are going to go to the pore, to the codification of the pore distribution of the pore statistics, and to apply it, to link it to the functional properties, not into histronics, but mainly in the applications for water condensation. Thank you very much for your attention.
I have two questions.
Okay.
First in the diagram of entropy versus scale. The scale is increasing or decreasing?
Increasing.
Increasing means you have final information.
No, more coarse. Coarse information.
So as
We are going to smoothing. That is.
the horizontal line is increasing, your image is more coarse.
Yes, since we average the information, that is the pixels of the image, we are getting more smooth images, smoother images. This is why the entropy goes down.
Yes. Scale increase is coarser representation.
Coarser and average. Average.
Yes.
So we take a window which scale is increasing.
Yes. For small scale, you have the largest entropy.
Correct.
Right?
Because we will have more information.
Yes. It means that our distribution is the same. You only take the average as you progress in the scale.
The probability distribution,
This probability distribution becomes coarser and coarser.
yes, more narrow. Yes.
Yes. Then you have a monotonic decrease of
Not always. I show that in cases where you. This is an example. But what do we have in this? Just a moment. When we have periodic patterns, we have these oscillations.
because, as you know, in general, standard entropy is decreasing if you increase the scale.
This is what's happening. Yes. This is a typical case, but when you have some period.
The fact that you violate this general theory so that as you go down the scale, some new effect appears. It's as if the new probability is not just the average, it's just you have a sort of emergence.
This is the periodicity. This is the periodic structure. Yeah, of course. This is the emergence is the emergence of the specific periodic structures you have. That is, you don't have. Yes.
So in this way, you have a clear way to quantitatively assess emergent phenomena.
Yes, of course.
The second question is the moral patterns that you classify. You are doing supervised learning, it means you have given patterns and you identify what is happening. Or not.
Yes, correct.
You don't know the patterns, you just
We synthetic
if they match or do not match.
Correct.
So it is supervised learning. Thank you very much.
I thank you. Yes. You are welcome.
Question. If you apply this to amorphous materials present short range order, wide range order. If you apply this, it is experimental.
Yes. Some applications of this are on amorphous polymer materials.
Without relations.
Without in amorphous materials, we have the scenario of entropy going down versus scale because we don't have. Yes.
Any other questions? Also, let's take with this speech, we reach the end of this session. There will be a closing ceremony in this room.
Yes, no.
Because there are also panelists. So I think perhaps if you want to vote for taking
Don't we have one more presentation? Yeah, for coffee, you can yes, 15 minutes and you can close. Yeah, I already sent to Slavo Can I change Okay, it's better. I understand. Okay. I already Başlayalım mı Stalin? Okay. No. Okay, let's start the finishing or closing ceremony. Dear colleagues, distinguished guests, and dear friends, as we come to end of the International Interdisciplinary Chaos Symposium, I would like to thank all of you for being here. Before we close, I would like to look back at the journey of our symposium. The Chaos Symposium has grown over the years. It started in 2006, followed by the meeting in 8, 10, 12, 19, and 25. Finally, we are here at 2026. Each symposium has brought together researchers from different countries and different fields. It has become a place where the people share ideas, learn from each other, and start new collaborations. Today, we are proud to continue this tradition. What started as a scientific meeting has grown into an international committee connected by curiosity and a shared interest in chaos and complex systems. During the last 3 days, we have listened to excellent presentations, shared our research, asked important questions, and learned from one another. It has been wonderful to see researchers from many different disciplines working together. I would like to thank our keynote speakers, invited speakers, session chairs, member of the scientific and organizing committees, our volunteers, and every participant. Your support, hard work, and valuable contributions made this symposium possible. Special thanks go to Professor Stavronidis and Professor Demetrios for their great effort in organizing this symposium. I also hope you enjoy your time here in Athens. It has been a great place to meet, exchange ideas, and build new friendships. Although the symposium ends today, I hope the conversations started here will continue. Maybe you found a new research idea, a new collaborator, or a new field and friend. I hope these connections will continue long after you leave Athens. Before we finish, I would like to give you a chance to speak. If you have any comments, ideas, or suggestions about the symposium, we would be happy to hear them. Would anyone like to speak a few words about the symposium? No? Anyone? Okay.
Ses.
It is my second time in this conference. I believe it's a very nice opportunity to discuss with people from different fields. Last year, I heard two things and we made two proposals with it. This year, I heard something else. So it's a good thing, I believe. It was very fruitful discussions. And also, I think that the organization was very, very good. So next time, well, where will it be? Is it? We'll see. Okay, we are waiting for the next year. Congratulations.
Thank you very much. You know, it is not easy to organize a conference or symposium. It takes a long time and a lot of duties. Really, I am very happy to work with Professor Stavridis and Professor Demetrios. They helped too much for this year. Thank you very much. Any other wants to tell anything about the? No? You? Maybe a few words? Okay, after that we will close it.
After that we close. I want to thank you all for being here. I want to thank, as I said in the opening ceremony, all those that contributed, not only with the invited talks, not only with the support for organizing this whole thing, and the scientific part, for helping with the scientific part, but also everyone that has submitted a paper here and attended this conference. So I want to thank Professor Demetrios, Nufio company that helped us here, because, you know, I'm not living in Athens and it's difficult to coordinate things. Professor Demetrios had put a huge effort on this, also with Nufio. And I look forward for the next edition next year, which most probably is going to be in Palma. Not for sure yet, but most probably. Yes, please.
It's a good opportunity also for me to say thank you again for the perfect organization, for the great hospitality, organizing the transportation and everything, but also to everybody who gave a talk here. I think it was interesting. It was a very broad spectrum of topics. But this brings you also in contact with something you haven't seen before, maybe, or would never see, because you would not read all the articles, of course. So this is always disturbing your mind. But this is, for me, always good when I go home from a conference and I have a few notes with some new ideas. If one idea is successful, then the conference was successful. So thank you very much, and good luck for the next.
Okay, no more, I think. Okay. Thank you for your comments and suggestions. We really appreciate your feedback. Finally, thank you once again for being a part of the International Interdisciplinary Care Symposium. We hope you had a good time in Athens. Have a safe journey to home, and we hope to welcome you again at the next Chaos Symposium. Thank you very much. Efaristo Parapoli Yaola. Thank you.